Welcome to my channel Physics with Akash Goel. In this video I am taking a problem on hidden thermodynamics from Pathfinder. Problem statement is, if ratio of efficiencies of two processes A and B shown in the PV indicator diagram is K, find the efficiencies individually for process A and for process B. The working substance in this processes is 1 mole of an ideal monatomic gas. So this is one process and this is another process, and the ratio of efficiency in both the process is given, and we have to find the individual efficiencies in the two situations. So to find efficiency we use this relation. Efficiency of a cyclic thermodynamic process is given by work done by the system or work done by the gas divided by the heat absorbed or heat given to the gas during the process. So this is the heat absorbed by the gas or heat given to the gas. So this ratio represents efficiency, and for this process, for this cyclic process, the net work done is equal to the net heat after considering both heat absorbed and heat released. So this is basically the net heat during the process, and this is only heat absorbed during the process. For work done, we can directly find the area under this PV or area of this PV diagram, and this will be like this. This is this enclosed area, and obviously this is expansion work, and this is also this area. The pressure is not given, so we can assume pressure at this location is P1 and pressure at this position is P2. So individually let us find the expression of efficiencies for both the process, and for that we have to find work done and heat absorbed in both the process. So let us start with the process A. So I am first taking process A. So calculation for process A, work done in process A is equal to this area, and this side will be P2 minus P1, and the base is 3V minus 2V, that is equal to V. So this is work done in A. And what is heat absorbed? So during this cyclic process, which are the processes in which heat is absorbed? So the processes are like isochoric and isobaric. This is isochoric process, volume is constant at 2V. This is isobaric process, pressure is constant. This is again isochoric process, this is again isobaric process. In this process, volume is constant, pressure is increasing, that means temperature is increasing. And in isobaric and in isochoric process, heat exchanged can directly be written using formulas NCP delta T for isobaric process and NCV delta T for isochoric process. So if temperature increases, heat is positive, that means heat is absorbed. So in this process heat is absorbed, and in this process heat is absorbed, and in this process heat is released. So in delta T is negative, temperature is decreasing, heat is released. And in this process also pressure is constant and volume is decreasing, that means heat is released. So we have to find heat related to this process and this process. So let us find heat, and Cp and Cv values and number of moles given the problem is equal to 1, and the values of Cp and Cv. So Cv is Fr by 2, this is degree of freedom, gas constant divided by 2, degree of freedom is 3, so this is 3R by 2 for monatomic ideal gas. The value of Cp is just C plus R, this is 5R by 2. So these are the values of Cp and Cv. So heat absorbed in process A. So for this process we can use NCV delta T, and for this process we can use NCP delta T. So N is 1, Cv is 3R by 2, 3R by 2, and change in temperature in this particular process. So change in temperature, let us assume this change in temperature is delta T1, and suppose this change in temperature is delta T2. So this is simply delta T1. And for the other process 5R by 2 NCP delta T, this is delta T2. we can write R delta T1, R delta T2 in terms of pressure and volume. Since from ideal gas equation PV is equal to RT, and if we take differentials, delta PV is equal to R delta T. So in this process, volume is constant. If volume is constant, so this is V delta P. So V delta P, this is equal to R delta T in this process. And for this process, pressure is constant, so this will be, P will come out, and P delta V is equal to R delta T. So accordingly we have to write equations like this. So for this process, volume is constant, and volume is constant at 2V. And what is the change in pressure? Change in pressure is P2 minus P1 plus 5 by 2. For R delta T I have written this R will go from here, R will not come here. 5 by 2 for R delta T2. In this process, pressure is constant and volume is changing, and this is P2, and change in volume is 3V minus 2, this is V. So this is the expression for heat. Now efficiency can be written as P2 minus P1 into V divided by this 2 and 2 will go, this is 3, V will come out as common, this is 3, P2 minus P1, and this is 5 by 2 P2. So this is the expression for efficiency in case of A. Let us find efficiency in case of B. So work done in the process B. Again, work done in the process B is change in this height, and in this base 5V minus 4V, this base is equal to V, and this height is equal to P2 minus P1. So this is P2 minus P1 into V. So work done is same in both the process, and heat exchanged. So again, this is isochoric process, and this is isochoric process, and taking clue from this this is 4V. Change in pressure is P2 minus P1. I am just using this expression to write this, and this is 5 by 2. The pressure here is again P2, and the change in volume is again V. So just like this I have written this, and this efficiency, like V is cancelled here V is also cancelled, P2 minus P1, and this is basically 6 times P2 minus P1, this will be 6 plus 5 by 2 P2. Now I have calculated the efficiency expression for process A, efficiency expression for process B. Now what is the information given? Information given is that the ratio of these two is equal to K. So the ratio is K. So eta A by eta B, this ratio is given as K. Now it may seem that the variables are more than the informations, the variables are more, and we have to find the efficiency eta and eta B, and for that we must know P1 and P2 both, and the information we are given is only one, that ratio is equal to K. So it may seem that the variables are more and information is less, but if we carefully observe mathematically, now it's all mathematical manipulations. So if we carefully observe, we can reduce our variable to one only. We can see there are two variables P2 and P1, but we can reduce these variables to one only. And how we can reduce these variables? You can just divide this expression. One option is you can divide this expression numerator and denominator by P1. If we divide this expression, then this will be P2 by P1 minus 1, and this is P2 by P1 minus 1. This is simply 1. So the whole expression will be in terms of P2 by P1, and again this whole expression will be in terms of P2 by P1. So there is only one variable. One more thing we can do. The method one is we can divide by P1, or other thing we can do is we can divide numerator and denominator by P2 minus P1. This can also be done. I'm going with this. I'm dividing the whole expression numerator and denominator by P2 minus P1. So this is simply equal to 1, this is simply equal to 1, and here we have P2 divided by P2 minus P1. Again here we have P2 divided by P2 minus P1. So P2 divided by P2 minus P1 I can take as some variable equal to x. So this eta A by eta B is equal to k. This equation I can use like this. I can use this equation like this. This eta A can be written as, after dividing all this, this eta A I can write it like this: 1 divided by 3 plus 5 by 2x. Now this eta B I can write it like this: 1 divided by 6 plus 5 by 2 into x. And after dividing I can get eta A by eta B, this is equal to 6 plus 5 by 2x divided by 3 plus 5 by 2x, and this ratio is given as k. From here I can find the value of x. I can find the value of x from this equation, and this x will come out as, x will be given by 6 by 5 on calculation, k minus 2 divided by 1 minus k. This is the value of x from here. And if I calculated x, I can put this x in any of these expressions. If I have to find eta A, then I can put x in this expression. If I have to find eta B, then I can put x in this expression. So putting x in these expressions, I can easily find the value of eta and eta B. So eta A can be found like this. After putting x, this will be equal to k minus 1 by 3, and eta B is obviously k minus 1 by 3k. So just put this expression into this and find eta A, and if you find eta A, then you can easily find eta B using this ratio. So here it is just mathematical manipulation. On physics part it is simple. We have to just apply the concept of efficiency of a cycle, of a thermodynamic cycle, and after that we have to apply mathematics also, calculations we have to do, and in such a manner that it may occur that it may seem that variables are more, but we can just manipulate these equations such that we can arrive what is asked in this question.